Welcome back to this next video in which we are discussing double dual vector spaces. Okay, so we've seen the definition of a double dual vector space. It's just the dual vector space of the dual vector space. Okay, and that's the definition that applies whether you're dealing with finite dimensional vector spaces or infinite dimensional vector spaces. However, what we're now doing is we're just looking at V as a finite dimensional vector space, because here the theory becomes very simple, because actually the double dual vector space is exactly equal to the initial vector space V, and the vector space and its dual vector space are beautifully engaged in this pair. Okay, so one represents the linear maps onto the field F of the other. Okay, so what we're doing is trying to understand that statement in more detail. Okay, so far what we've succeeded in doing is taking an arbitrary element of the initial vector space V and associating with it a linear map from the dual vector space into the field, which therefore will be in the double dual vector space. What we now want to do is go in reverse. We want to take an arbitrary element of the double dual vector space and show that we can associate with that an element of the original vector space, for which this element of the double dual vector space is actually just the evaluation function for that. Okay, so how are we going to do this then? Okay, so what we're going to do is we're going to take some arbitrary zeta, so let zeta be an element of the double dual vector space. Okay, so zeta is some arbitrary element of the double dual vector space. Okay, so just to make this utterly clear then, zeta will be mapping the dual vector space onto the field capital F, and it will be a linear map. Okay, so it will be able to take in any covector in the dual vector space and send it onto some element of the field. Okay, now let's just explore this in a little bit more detail. So let's consider what is zeta of phi. Okay, what I would like to be able to do is show that zeta of phi is equal to phi evaluated at some vector from the original vector space capital V. And the best way, in my opinion, of doing this is by putting a basis onto our initial vector space capital V and then putting the dual basis onto the dual vector space. Okay, so let's just go up here then, and let's say onto the original vector space here, which is now a finite dimensional vector space, I put some basis B, which is V1, V2, all the way up to Vn. Okay, so here is some arbitrary basis, and the dimension of this finite dimensional vector space is just little n there. Okay, so that's the basis for that one. And then what we're going to do is equip the dual vector space with the dual basis here, B star, which will have the basis vectors V1 star, V2 star, all the way up to Vn star, which we defined in the previous video on this playlist on vector spaces. Okay, and remember, just to remind you, these dual basis vectors here, these are the linear maps which send all vectors in this original vector space onto their corresponding coordinates with respect to this basis in the field. Okay, so for instance, V1 star, that would send every vector onto its first coordinate, its scalar coefficient in front of the first basis vector V1 here. Okay, V2 star, that would send any vector just onto its second coordinate, the scalar coefficient that would be in front of the second basis vector here if we produced its linear combination in terms of the basis vectors. Okay, so that's how these dual basis vectors are defined in terms of the basis that we have on the initial vector space. Okay, right. Now, we know that any covector in the dual vector space can be written as a linear combination of our dual basis vectors, so we'll do that for phi here. Okay, and this works very nicely because the linear combination that phi will actually be represented as according to these dual basis vectors will look like this. The scalar coefficients in front of them, each of the basis vectors, will be phi of V1, phi of V2, phi of all the way up to Vn. So let me just write this out. So we'll have phi is equal to phi of V1 times V1 star plus phi of V2 times V2 star plus all the way up to phi of Vn times Vn star. like so. Okay, so if you expand an element of the dual vector space in terms of the dual basis vectors, then the scalar coefficients that end up in front of the dual basis vectors here, these are exactly the scalar coefficients in the field that the basis vectors from the first basis vector would be mapped onto by your mapping phi. Okay, so any linear map from the initial vector space V to the field capital F is completely and utterly determined by where it sends the basis vectors in the field. Okay, and we are now sticking that information in here, and it works absolutely perfectly if you do indeed define these dual basis vectors in the way that I've shown you. And I should stress that these additions and scalar multiplications that we've got here, these are all done in our dual vector space. So all of those additions are in the dual vector space, all of these scalar multiplications are in the dual vector space. So this is the linear combination that any covector can be expanded as. And as I say, the coefficients in front of these dual basis vectors will just be exactly where this covector phi sends each of the basis vectors in the initial vector space onto in the field capital F. Okay, now why is that so important? And I should stress, if you want to see more about where this comes from, it's all discussed in more detail in the previous video on basis of a dual vector space. Okay, so why have I done this? Well, we can now put in the linear combination that I've written phi as into this expression here. Okay, so I'll now get that zeta of phi is equal to zeta of all of this. So we'll get phi of v1 times v1 star plus phi of v2 times v2 star plus all the way along to phi of vn times vn star, like so. Okay, now of course this is a linear map. So this respects linear combinations. It's a linear map from the dual vector space into the field capital F. So it's going to respect linear combinations in the dual vector space. So what this will actually become is the scalar coefficients will all come out. The addition will all split up. So this will actually end up as becoming phi of v1 times zeta of v1 star, like so, plus phi of v2 times zeta of v2 star plus all the way along to phi of vn times zeta of vn star, like so. Now let's add a bit of colour on here so that we get this completely straight. Okay, so remember all of these operations here were done in the dual vector space. So this was multiplication in the dual vector space, addition, multiplication, all of that was in the dual vector space. Because zeta here is a very special map, it's a linear map from the dual vector space into the field capital F, it means that it will respect this linear combination. Okay, so it will just become this, where all of these multiplications and additions here now are done in the field. Okay, so everything has now become to do with the field. So we can see here that the mapping zeta, this linear map in the double dual vector space, is completely and utterly determined by where it sends the dual basis vectors of the dual vector space. Okay, so where it sends v1 star, v2 star, all the way up to vn star. But let me stress, those will just be elements of the field. They will just be scalars. So let me change my notation now. Let me call this A1, let me call this A2, and so on, all the way up to AN. So I'm just changing my notation so that it looks simpler. But remember, these things here, they are just elements of the field. Nothing more, they're nothing more scary than that. Okay, and every single different zeta will have a different combination of these. It will send the dual basis vectors onto different elements of the field overall. Okay, so every single different element of the double dual vector space will have a different combination A1, A2, all the way up to AN, because as I say, these completely determine the entire linear map. So if they had exactly the same numbers in all of these positions, then they'd be the exact same linear map. Okay, so every single one of them will just have some combination, and we can get that, and these are just scalars, so you can work these out for any linear map in the double dual vector space. And now what I can do is rewrite this like so. It's just a1 times phi of v1 plus a2 times phi of v2 plus all the way along to an times phi of vn, like so. Okay, where all of these additions and multiplications are done in the field. Okay, but phi here, phi was a linear map from the initial vector space capital V to the field capital F. So what does this look like? This looks like I've just taken phi of a linear combination in my initial vector space. So what I can rewrite this actually as is phi of a1 times v1 plus a2 times v2 plus all the way up to an times vn. So I'm doing the exact reverse now. Here I went from this to this, and now I'm going in the exact reverse direction and taking it back all in like this. Okay, I'm now using the fact that phi is a linear map here from the vector space capital V to the field capital F. Okay, so everything we've got in here now will now be done in our initial vector space capital V. So let me just move this up a bit. So this will be scalar multiplication in our initial vector space capital V. This will be addition, scalar multiplication, addition, addition, scalar multiplication, all in the initial vector space capital V. Now, here, a1 v1 plus a2 v2 plus all the way along to an vn, that's just some vector, a unique vector in my initial vector space capital V. Okay, so I have now managed to express zeta of phi as being phi of some vector v in my initial vector space capital V. I have shown that you can always take any element of the double dual vector space and think of it as an evaluation map. Okay, in this case, this specific combination. In fact, I've even told you how to actually find the vector. What you need to ask is, where does zeta send all of the dual basis vectors of the dual vector space onto? Those will be elements of the field. Then just stick those in front of all of the basis vectors in the initial vector space to get the correct linear combination, which will give you this vector in the initial vector space, which this zeta can be thought of as the evaluation function associated with that element. Okay, so that's how you can take any element of the double dual vector space and think of it as having, well, as an evaluation function where you're just evaluating all of the covectors at this certain vector. Okay, and for each different zeta, you will get a different combination, a1, a2, all the way up to an, and therefore, because this is a basis, all these different linear combinations give different vectors in the initial vector space, so every different element of the double dual vector space will have a different vector in the initial vector space that it's associated with, and we know that it goes the other way around. We know that every single vector in the initial vector space can be thought of as being associated with an evaluation function which is in the double dual vector space. So we're beginning to see that this works both ways around and that there's probably a bijection between the two, and that's the next great thing that I want to say. Okay, so the next thing that I want to show is that there is a very specific isomorphism between the double dual vector space and the initial vector space, okay? So we're going to now find an isomorphism which we'll call F from the double dual, whoops, that should be double dual vector space, to the initial vector space capital V. Now you might say, but what's the point? You've already argued that the double dual vector space is isomorphic to the initial vector space. And I would agree, yes, we have already shown that the double dual vector space is isomorphic to the initial vector space. However, I want to establish a very specific isomorphism. Okay, to say that they are truly equal to one another, I want a very special isomorphism, where I am just finding an isomorphism which will take any element of the double dual vector space and it will just associate it with this vector in the initial vector space, which that element of the double dual vector space can be thought of as being the evaluation function for. Okay, and that special bijective map, I want to prove that that specifically is an isomorphism, and that's not trivial. Although we have agreed that they will be isomorphic, that there will be isomorphisms between them, we haven't agreed that this is a specific isomorphism between them. So I want to show that it is indeed a specific isomorphism, and then I will say, okay, let's think of them as being truly equal to one another. Okay, right, so how is this going to work? Well, I've just said how it's going to work. It's going to take any element of the double dual vector space, any zeta in the double dual vector space, and it's going to map it onto this vector v such that we can think of zeta as being the evaluation function for v. Okay, so I've just shown you how to get this v. If you have some zeta, you just need to know where does zeta send those dual basis vectors to. Okay, right. So what we now need to show then is that this map is indeed an isomorphism. So I hope I've already convinced you that it is going to be a bijective map, because I've shown you that every single element here will be carried to a unique element here. So it is one-to-one, because I gave you that argument that all of the zetas would have different specific combinations of elements of the field, A1, A2, all the way up to AN, and therefore when you take this linear combination, they'll all have distinct elements of the initial vector space. So that's the one-to-one. It's also onto, because initially I argued that any vector in the initial vector space can be associated with an evaluation function, which will be an element of the double dual vector space. So every single one of these must get some element in the double dual vector space being mapped onto it. So that's how we can show it's one-to-one and onto, and therefore it's bijective. What we now want to show is that it actually is an algebraic isomorphism. Okay, so what I need to show you then is that f of, let's say, zeta 1 plus zeta 2, okay, where this now is addition in the double dual vector space, and this is where things can get really, really confusing if we're not careful with the color coding. So I will represent now addition in the double dual vector space with yellow here. Okay, so this is addition in the double dual vector space, and it's represented in yellow there. Okay, and I want to show that this is the same as f of zeta 1 plus f of zeta 2, where this second addition here is addition in the codomain, which will be the initial vector space. Okay, now what color was I coding things in the initial vector space in? Orange. Okay, so this needs to be addition in the initial vector space, so we'll have it in orange there. And then we'll also need to prove the same thing for scalar multiplication. Okay, so how are we going to do this? Well, we firstly need to just think about this map, which is zeta 1 plus zeta 2. We haven't really talked about how addition is going to work in the double dual vector space. It's going to be defined exactly how we defined addition in the dual vector space, but let's explore that in a little bit more detail. Okay, so zeta 1 plus zeta 2 then. Okay, where this is the addition in the double dual vector space. This is going to be some other element of the double dual vector space, and elements of the double dual vector spaces are functions of the dual vector space. Okay, so this is going to work on some phi. Okay, and what I'd like to do is think about what element of the vector space, capital V, is this going to actually be the evaluation function for? What's the element of the vector space which we can associate with this? Now, firstly, actually, it's probably worth going to this side here, because f, remember, is just this function which takes any element of the double dual vector space and maps it onto this vector in the initial vector space, which we can think of it as being the evaluation function for. Let's say that f of zeta 1 we call v1. Okay, so let's just say that the vector which is associated with zeta 1 is v1, and let's say that the vector that's associated with zeta 2 is v2. We'll use v1 and v2 in a moment. Okay, they'll pop up in a moment. Now, back to the other side. So switch from that back to the other side now. let's consider what the definition of this is going to be equal to. So how do we define addition in a dual vector space? Because we're going to have to do the same thing now for the double dual vector space. Okay, so the way we define this is we say, okay, we know something about the mapping zeta 1, we know something about the mapping zeta 2, so just say zeta 1 will map phi onto some element of the field. Zeta 2, oh whoops, messed it up there, zeta 2 will map phi onto some element of the field. Just take those two things that these two zetas add, take them onto in the field, and add them together here in the field. That's the way that we define addition in a dual vector space. Okay, yes, we're now working in the double dual vector space, but the way we'll define addition is exactly homologous to how we did it for the dual vector space, and that is how we did it for the dual vector space. Okay, right. Now, zeta 1 of phi, what will that actually be equal to? Well, zeta 1 of phi, we know that zeta 1 is associated with this vector v1 here. So it will just map phi exactly onto phi evaluated at v1. Okay, remember, zeta 1 can be associated with this vector. We know all elements of the double dual vector space can be associated with vectors. Okay, so zeta 1 of phi is just going to be exactly phi evaluated at v1, because I said up there, let's say that the vector that's associated with zeta 1, the vector which it represents the evaluation function of, is called v1. So this will just be equal to phi of v1. Okay, now leave that addition sign in there here. Okay, and now the other bit, zeta 2 of phi, same argument again. Okay, that's just going to be phi evaluated at v2, because I said let v2 be the vector associated with zeta 2, the vector which zeta 2 is effectively the evaluation function of. So now I can just say that zeta 2 will map phi onto phi of v2, okay, because it is just the evaluation function associated with v2. Now, phi, remember, is a linear map from the initial vector space into the field capital F. So what can we do here? We can apply it being a linear map in reverse here, and we can say that this will be the same as phi of v1 plus v2. Okay, so I have now written zeta 1 plus zeta 2 of phi as phi of v1 plus v2, where, whoops, that's color-coded in wrong there. I do apologize, that should be coloured in orange, where those two are added together in the vector space, the initial vector space, and hopefully you'll agree that because phi is a linear map from the initial vector space into the field, that this is perfectly valid here. So I've now gone from this thing initially right down to here. I've written this thing here as an evaluation function where we're evaluating phi at this element of the initial vector space, which is v1 plus v2. But that's exactly what I wanted to say, that this element of the double dual vector space would be associated with, because if I look at this side, I'm saying that I want to associate it with v1 plus v2 in the vector space, but I've just shown that zeta 1 plus zeta 2 would be associated with the vector v1 plus v2. So indeed f will map zeta 1 plus zeta 2 onto v1 plus v2. So I've just done exactly what I wanted to do. Okay, right. So a very much so analogous argument now for scalar multiplication. So if you didn't fully understand that, we're going to do something very similar for scalar multiplication now, slightly easier. Okay, so now let's show that f of c times, and now we only need one zeta, so I'll just call it zeta rather than subscripting it with some number. Okay, we want to show that this is c times f of zeta. Okay, now let me colour in the different compositions here. This is scalar multiplication in the double dual vector space, whereas of course this is scalar multiplication in the initial vector space, so I'll colour that in orange. Okay, so if we want to show that this is truly an isomorphism, we now need to show this one. We've shown that it is an isomorphism with respect to addition, we've shown it's a bijective map. This is the final thing, we need to show that it's an isomorphism with respect to scalar multiplication. Okay, right. So how are we going to do this? Okay, well, very much so the same argument as we took here. So let's consider again, well actually firstly I'll do what I did here. Let's say that f of zeta, we will just call that v right at the start. So zeta is some element of the double dual vector space, okay? So it will have an element of our initial vector space associated with it for which it is effectively the evaluation function. Okay, let's call that v. Okay, so we want to show that this is just going to be c scalar multiplied with v in our initial vector space, so in orange there. Okay, so now let's work on the left-hand side here. So, c scalar multiplied by zeta, let's think more about that. So that's going to be some other element of our double dual vector space, and it's going to work on phi. Okay, which is a covector in the dual vector space. Okay, so I'll once again colour that scalar multiplication in yellow there. Okay, and once again we want to play around with this, get a bit more intuition for it, and try and end up with something that has this written out nice and explicitly as phi evaluated at something, hopefully c times v. Okay, so let's firstly then apply the definition for how scalar multiplication is going to work in the double dual vector space. So the way that we defined this for dual vector spaces is now just going to be carried over to this. Okay, so it's going to be c times zeta of phi, where this multiplication on this side is just multiplication in the field. So if you want to know where this element of the double dual vector space, c times zeta, is going to map any phi, you just say, well, where does zeta map phi, and scalar multiply that, or rather, sorry, this is in the field, so just multiply that by c. Okay, so that's how we define scalar multiplication in the double dual vector space. Okay, now, zeta of v. We've already said that zeta is going to be associated with the vector v, so that means that zeta of v is just going to be phi evaluated at v, because zeta is just the evaluation function for this vector v here. Okay, so now what we have got is c multiplied in the field by phi of v, but now again you remember the fact that phi is a covector, it's a map from the initial vector space into the field capital F, and what we can now do is swallow that c into here. Okay, so we'll get that this is phi of c times v, where this is now multiplication inside the vector space capital V. Okay, so it's scalar multiplication inside the vector space capital V. And therefore, of course, we have taken this thing and we have turned it into phi evaluated at some element of our initial vector space capital V. Okay, and it's exactly the element of the initial vector space that I wanted here. So I have shown that f of c times zeta, the element of the initial vector space associated with c times zeta in the double dual vector space, is going to be c times v, where v is the element associated with just zeta alone. Okay, so indeed, scalar multiplication in the double dual vector space is isomorphic to scalar multiplication in the initial vector space. So there is this beautiful, beautiful isomorphism between the initial vector space and the double dual vector space, where all the vectors in the initial vector space are carried onto evaluation functions, where you can evaluate all of the covectors at that actual vector of the initial vector space. So, what we will now say is, because there is this beautiful isomorphism, this incredibly natural isomorphism, we will now just think of the double dual vector space as being equal to the initial vector space, and we will think of the elements of the initial vector space as representing these linear maps of the dual vector space onto the field capital F. Okay, and that is where I'm going to leave you, with this beautiful duality between a vector space and its dual, this beautiful symmetry that each of them represents the linear maps of the other onto the field capital F. Okay, and that's where we'll end this video.